development, to control the assembly process, and to aid debugging. Some are column-oriented, with specific fields in specific columns. This was very common for machines using punched cards in the 1950s and early 1960s. Some assemblers have free-form syntax, with fields separated by delimiters, for example, punctuation, white space. Some assemblers are hybrid, with, for example, labels, in our specific column and other fields separated by delimiters. This became more common than column-oriented syntax in the 1960s. IBM System/360. All of the IBM assemblers for System/360, by default, have a label in column 1, fields separated by delimiters in columns 2 to 71, a continuation indicator in column 72 and a sequence number in columns 73 to 80. The delimiter for label, opcode, operands and comments is spaces, while individual operands are separated by commas and parentheses. Terminology. A macro assembler is an assembler that includes a Mach1 instruction facility so that parameterized assembly language text can be represented by a name, and that name can be used to insert the expanded text into other code. Open code refers to any assembler input outside of a macro definition. A cross-assembler, see also cross-compiler, is an assembler that is run on a computer or operating system, the host system, of a different type from the system on which the resulting code is to run, the target system. Cross-assembling facilitates the development of programs for systems that do not have the resources to support software development, such as an embedded system or a microcontroller. In such a case, the resulting object code must be transferred to the target system, via read-only memory, ROM, EPROM, etc. A programmer, when the read-only memory is integrated in the device, as in microcontrollers, or a data link using either an exact bit-by-bit copy of the object code or a text-based representation of that code, such as Intel Hex or Motorola S-Record. A high-level assembler is a program that provides language abstractions more often associated with high-level languages, such as advanced control structures, if /then/else do case, etc., and high-level abstract data types, including structures /records, unions, classes, and sets. A microassembler is a program that helps prepare a microprogram, called firmware, to control the low-level operation of a computer. A meta-assembler is a program that accepts the syntactic and semantic description of an assembly language, and generates an assembler for that language, 12, or that accepts an assembler source file along with such a description and assembles the source file in accordance with that description. Meta-symbol assemblers for the SDS9 series and SDS Sigma series of computers are meta-assemblers. 13, NB3. Sperry UNIVAC also provided amateur assembler for the UNIVAC 1100/2200 series. 14. Inline assembler, or embedded assembler, is assembler code contained within a high-level language program. 15. This is most often used in systems programs which need direct access to the hardware. Key concepts. Assembler. An assembler program creates object code by translating combinations of mnemonics and syntax for operations and addressing modes into their numerical equivalents. This representation typically includes an operation code, opcode, as well as other control bits and data. The assembler also calculates constant expressions and resolves symbolic names for memory locations and other entities. 16. The use of symbolic references is a key feature of assemblers, saving tedious calculations and manual address updates after program modifications. Most assemblers also include macro facilities for performing textual substitution. For example, to generate common short sequences of instructions as inline, instead of called subroutines. Some assemblers may also be able to perform some simple types of instruction set specific optimizations. One concrete example of this may be the ubiquitous x86 assemblers from various vendors. Called jump sizing, 16, most of them are able to perform jump instruction replacements, long jumps replaced by short or relative jumps, in any number of passes, on request. Others may even do simple rearrangement or insertion of instructions, such as some assemblers for ISC architectures that can help optimize a sensible instruction scheduling to exploit the CPU pipeline as efficiently as possible. 17. Assemblers have been available since the 1950s. As the first step above machine language and before high-level programming languages such as Fortran, Algol, COBOL and Lisp. There have also been several classes of translators and semi-automatic code generators with properties similar to both assembly and high-level languages, with speed code as perhaps one of the better-known examples. There may be several assemblers with different syntax for a particular CPU or instruction set architecture. For instance, an instruction to add memory data to a register in a x86 family processor might be addx, EBX, in original Intel syntax, whereas this would be written addl, %EBX, %. X in the AT and T syntax used by the new assembler. Despite different appearances, different syntactic forms generally generate the same numeric machine code. A single assembler may also have different modes in order to support variations in syntactic forms as well as their exact semantic interpretations, such as FASM syntax, TASM syntax, ideal mode, etc., in the special case of x86 assembly programming. Number of passes. There are two types of assemblers based on how many passes through the source are needed, how many times the assembler reads the source, to produce the object file. 1 pass assemblers go through the source code once. Any symbol used before it is defined will require errata at the end of the object code, or, at least, no earlier than the point where the symbol is defined, telling the linker or the loader to go back and overwrite a placeholder which had been left where the as yet undefined symbol was used. Multipass assemblers create a table with all symbols and their values in the first passes, then use the table in later passes to generate code. In both cases, the assembler must be able to determine the size of each instruction on the initial passes in order to calculate the addresses of subsequent symbols. This means that if the size of an operation referring to an operand defined later depends on the type or distance of the operand, the assembler will make a pessimistic estimate when first encountering the operation, and if necessary, pad it with one or more. No operation instructions in a later pass or the errata. In an assembler with peephole optimization, addresses may be recalculated between passes to allow replacing pessimistic code with code tailored to the exact distance from the target. The original reason for the use of one-pass assemblers was memory size and speed of assembly. Often a second pass would require storing the symbol table in memory, to handle forward references, rewinding and rereading the program source on tape, or rereading a deck of cards or punched paper tape. Later computers with much larger memories, especially disk storage, had the space to perform all necessary processing without such rereading. The advantage of the multipass assembler is that the absence of errata makes the linking process, or the program load if the assembler directly produces executable code, faster. 18. Example, in the following code snippet, a one-pass assembler would be able to determine the address of backward reference BKWD when assembling statement S2, but would not be able to determine the address of the forward reference FWD when assembling the branch statement S1. Indeed, FWD may be defined. A two-pass assembler would determine both addresses in pass 1, so they would be known when generating code in pass 2. S1 BFWD. FWDEQU asterisk. BKWDEQU asterisk. S2B BKWD. High-level assemblers. More sophisticated high-level assemblers provide language abstractions such as high-level procedure /function declarations and invocations. Advanced control structures, if /then /else, switch. High-level abstract data types, including structures /records, unions, classes, and sets. Sophisticated macro processing, although available on ordinary assemblers since the late 1950s for example, the IBM 700 series and IBM 7000 series, and since the 1960s for IBM System /360, S/360, amongst other machines. Object-oriented programming features such as classes, objects, abstraction, polymorphism and inheritance. 19. See language design below for more details. Assembly language. A program written in assembly language consists of a series of mnemonic processor instructions and metastatements, known variously as declarative operations, directives, pseudo-instructions, pseudo-operations and pseudo-ops, comments and data. Assembly language instructions usually consist of an opcode mnemonic followed by an operand, which might be a list of data, arguments or parameters. 20. Some instructions may be implied, which means the data upon which the instruction operates is implicitly defined by the instruction itself. Such an instruction does not take an operand. The resulting statement is translated by an assembler into machine language instructions that can be loaded into memory and executed. For example, the instruction below tells an x86/IA32 processor to move an immediate 8-bit value into a register. The binary code for this instruction is 10,110 followed by a 3-bit identifier for which register to use. The identifier for the L register is 000, so the following machine code loads the L register with the data 011000001. 20. 1011000001100001. This binary computer code can be made more human-readable by expressing it in hexadecimal as follows. B061. Here, B0 means move a copy of the following value into L, and 61 is a hexadecimal representation of value 01100001, which is 97 in decimal. Assembly language for the 8086 family provides the mnemonic MOV, an abbreviation of move, for instructions such as this, so the machine code above can be written as follows in assembly language, complete with an explanatory comment if required, after the semicolon. This is much easier to read and to remember. MOV L, 61H, load L with 97 decimal, 61 hex. In some assembly languages, including this one, the same mnemonic, such as MOV, may be used for a family of related instructions for loading, copying and moving data, whether these are immediate values in registers, or memory locations pointed to by values in registers or by immediate, A.K. direct, addresses. Other assemblers may use separate opcode mnemonics such as L for move memory to register, ST for move register to memory, LR for move register to register, MVI for move immediate operand to memory, etc. If the same mnemonic is used for different instructions, that means that the mnemonic corresponds to for all different binary instruction codes, excluding data, for example the 61H in this example, depending on the operands that follow the mnemonic. For example, for the x86/IA32 CPUs, the Intel assembly language's syntax MOVL R represents an instruction that moves the contents of register R into register L. The NB4 hexadecimal form of this instruction is 88E0. The first byte, 88H, identifies a move between a byte-sized register and either another register or memory, and the second byte, E0H, is encoded with 3-bit fields to specify that both operands are registers. The sources are, and the destination is L. In a case like this where the same mnemonic can represent more than one binary instruction, the assembler determines which instruction to generate by examining the operands. In the first example, the operand 61 is a valid hexadecimal numeric constant and is not a valid register name, so only the B0 instruction can be applicable. In the second example, the operand R is a valid register name and not a valid numeric constant, hexadecimal, decimal, octal, or binary, so only the 88 instruction can be applicable. Assembly languages are always designed so that this sort of unambiguousness is universally enforced for the syntax. For example, in the Intel x86 assembly language, a hexadecimal constant must start with a numeral digit, so that the hexadecimal number, equal to decimal 10, would be written as 0R or 0R not R, specifically so that it cannot appear to be the name of register R. The same rule also prevents ambiguity with the names of registers BH, CH, and DH, as well as with any user-defined symbol that ends with the letter H and otherwise contains only characters that are hexadecimal digits, such as the word beach. Returning to the original example, while the x86 of code 1011000, B0, copies an 8-bit value into the AL register, 1011001, B1, moves it into CL and 1011010, B2, does so into DL. Assembly language examples for these follow. 20, MOVL, 1H, load L with immediate value 1. MOVCL, 2H, load CL with immediate value 2. MOVDL, 3H, load DL with immediate value 3. The syntax of MOV can also be more complex as the following examples show. 21, MOVEAX, EBX, move the 4 bytes in memory at the address contained in EBX into EAX. MOV, ESI plus EAX, CL, move the contents of CL into the byte at address ESI plus EAX. MOVDS, DX, move the contents of DX into segment register DS. In each case, the MOV mnemonic is translated directly into one of the opcodes 88-8C, 8E, A0, A3, B0, BF, C6 or C7 by an assembler, and the programmer normally does not have to know or remember which. 20. Transforming assembly language into machine code is the job of an assembler, and the reverse can at least partially be achieved by a disassembler. Unlike high-level languages, there is a one-to-one correspondence between many simple assembly statements and machine language instructions. However, in some cases, an assembler may provide pseudo instructions, essentially macros, which expand into several machine language instructions to provide commonly needed functionality. For example, for a machine that lacks a branch if greater or equal instruction, an assembler may provide a pseudo instruction that expands to the machine's set if less than and branch if 0, on the result of the set instruction. Most full-featured assemblers also provide a rich macro language, discussed below, which is used by vendors and programmers to generate more complex code and data sequences. Since the information about pseudo instructions and macros defined in the assembler environment is not present in the object program, a disassembler cannot reconstruct the macro and pseudo instruction invocations but can only disassemble the actual machine instructions that the assembler generated from those abstract assembly language entities. Likewise, since comments in the assembly language source file are ignored by the assembler and have no effect on the object code it generates, a disassembler is always completely unable to recover source comments. Each computer architecture has its own machine language. Computers differ in the number and type of operations they support, in the different sizes and numbers of registers, and in the representations of data in storage. While most general-purpose computers are able to carry out essentially the same functionality, few are